Hello everyone, thanks for checking out this video. My name is Frank, and in this video I'll review a desktop tutorial on hyperspectral remote sensing that I've published on my website frankstutorials.nl. The tutorial is titled Mineral Mapping of the Palai area with hyperspectral remote sensing. I'll start with step 1, comparison of hyperspectral image and geological map. Start. The first thing in this tutorial is to open Hyperspectral Python, the hippie software. Then open an image viewer and display the hyperspectral image, which is this one. Okay. Try to fit the whole image in this window, and then we'll make a color composite of it, of bands 14 in red, 5 in green, and band 1 in blue. Okay, this is what the area looks like. Then we open another image viewer with the geological map of the same area. Also make a color image of it. Don't know why it is doing that. Make it approximately the same size as the hyperspectral image. And then I'll show it here, so that we can compare. The geological map has a legend. Which I'll display here. Now we can compare the hyperspectral image in natural colors and the geological map. And what you can see that in the geological map shows here volcanic rock, tertiary volcanic rock here as well. We cannot see it very clearly in this image, but we can see this big structure, for instance, running northeast southwest through the image, which is an active fault, which is the Carboneras fault. It's a strike slip structure. And on the left we can see here this limestone plateau, which is also from the tertiary. And to the north, some brighter tones are evaporite sediments, which are related to the Messinian crisis when the Mediterranean Sea dried up. Some limestone units here as well, and we have the stream bed. Fragments of the older rocks from Cretaceous up to Triassic can be found as slivers in this fault zone. And they come back here in some more darker tones. Okay, that's the end of step 1. I can close these windows, and we'll continue with step 2, mapping the wavelength position of deepest. To do that is we open the tools menu. First go to step 1, wavelength of minimum. So what we'll do here is calculate the deepest absorption features for each pixel in the wavelength range between 2100 and 2400 micrometers, nanometers, sorry. The input file is the hyperspectral image that we have already seen. It will automatically create an output called WAV2 because it's the second version of this wavelength mapper tool. We have to enter the right wavelength range in micrometers from 2.1 to 2.4. Number of features to match, we can leave it at 3. So it will look at, it will search for the 3 deepest absorption features in its wavelength range. Then we click run. It says running, please wait. And indeed, we have to wait because this is not the fastest of all tools. But that's good because so the window says completed. So the wavelength image is now created. That took about 4 minutes. If you have a faster computer, it will take less time, but it's not the fastest of all tools. Let's have a look at the result in an image viewer. So this is the image that was just created, and this is what it looks like. This is band 0 of this image, and it shows in gray tones the wavelength position of the deepest absorption feature. And you can see here in these gray areas, it's all around 2.296 micrometers. And here in the dark areas, it's around 2.20 something. Yeah, so those pixels you can see in dark tones. Band number 1, so the second band in this image, shows the depth of the absorption feature, of the deepest absorption feature. And here you can see that it ranges from approximately 0.05, so that's 5%, up to 0.21, which is about 21% depth. The next thing to do is to view the result in a scatter plot. Open the wavelength image again here. We want to plot the wavelength position on the x-axis, so that's band number 1, and the depth of the feature along the y-axis. So we click run, and then we get this result. So what you can see here is that there's a large cluster of pixels that has a wavelength position at 2.3. From shallow to deeper depths, there's a cluster here around 2.2. There's a small cluster just shorter than 2.4, and then there are 2 clusters here at around 2.34, 2.35 micrometers. So they can be related to different minerals having these different deepest absorption features. What will help now to interpret this is to show field spectra of some of the end members in this image. So I'll open Spectral Library Viewer. So this data was also provided for the exercise. Field spectra, it's in the folder field spectra, and these are 4 different materials that we found in the area. One is calcite, gypsum, illite, and some soil material. We can make a plot. Then we get this. What you can see here is illite, which has an absorption feature around 2.2, which is related to this cluster. So illite rich pixels can be found here. In blue is calcite, which has an absorption feature at 2.337, more or less. It varies a bit. That's related to this cluster here. And then we have this cyan-colored soil material, which doesn't have very deep absorption features, but they have a wavelength which corresponds to this cluster. The gypsum we'll ignore for now, but you can imagine, well, if it is shown in any of the pixel spectra, it's at a slightly longer wavelength than illite. All right. So now that we understand these clusters to some extent, we can make a wavelength map. So what we'll do is we combine the information in band 0 of the wavelength image, which is the wavelength position, with the depth of the absorption feature. We combine that in one image. I'll show you how to do it. So now you go to step 2 in the tools manual called wavelength mapping. And then we get a different dialog. Now we input the wavelength image here. It will automatically create another image which is called _map. We have to enter the right wavelength range, which was 2.1 to 2.4. The stretch for the depth of the feature we leave to 0 because then it will take an automated stretch based on the image statistics. We click run. This one is a bit faster, as you can see. Okay, it's completed and we can have a look at the result now. This one. So this is the resulting image. We have to make sure that the colors are not stretched, because we want to compare the colors with a lookup table that has also been created at the same time, which is this one. So this is the legend for this wavelength map, and it shows how the colors relate to the deepest absorption feature. And the intensity is shown along this x-axis, which is determined by or controlled by the depth of the absorption feature. Okay, and what we can see is that this cluster of pixels in green, which has a wavelength position at around 2.2, comes out very clearly. These pixels have relatively deep absorption features. That's why we get this bright color. And the color itself shows that the wavelength position is around 2.2. If we look at other parts of the image, we can see that many shades are orange or reddish, and that corresponds to wavelength positions between 2.3 and 2.35. Which is related to the soil material. Those are calcareous soils and calcite as well within the limestone. So that was the end of step 2, and then we'll continue with step 3, and we'll show the results in Google Earth. So the colorful image that we have just produced will now be exported to Google Earth. We open the tool Generate KML. This is the dialog box. We select the map, the wavelength map. We choose the band combination red band 0, green band 1, and blue band 2. No stretch. Otherwise we cannot correlate the colors anymore to the color table. The target is Earth. Click run. And then it's done. So let's have a look in the file Explorer. Here's the KML file. So we'll double click it. And it will be automatically opened in Google Earth. There we go, to Southeast Spain. Okay, so that's where we are. This is the Cabo de Gata area. You can see this big structure, the Carboneras Fault. The town of Carboneras is here. And here's our image. What you can clearly see is that this area here is highlighted, so that's where the illite minerals are found at the surface, and that is the target for any hydrothermal alteration deposit in this area. And you can see that this area, well, it's just east of the Carboneras fault and west of this stream bed. We can zoom in a bit further, and then we get a very nice view. So there is agricultural land as well, and the areas here in between, they have been strongly altered. The old mining shaft is also in this area, but there's no active mining anymore. That's something from the past. Okay, and there are some patches of illite-rich material here as well that come out very nicely. That's within the fault zone itself. Okay, that's the end of step 3. Well, let's leave it here open in Google Earth. Then there's one optional step in this exercise, that is to map also gypsum minerals using a different wavelength range. So that's what I'm going to show now, how to do that in step 4. And for that I have to follow the same procedure of wavelength mapping. So first I'll calculate the wavelength of the minimum, and then using a different wavelength range, I use the same hyperspectral image. Here I choose a different wavelength range between 1.65 and 1.82. And then the output I'll give a different name. Otherwise we cannot differentiate it from the other image that we produced earlier. Alright, click run. So that will take again a couple of minutes. In the meantime, we can have a look at the gypsum spectrum again in the spectral library viewer. So there it is. I'll make a plot of it. And this shows a nice gypsum spectrum, very typical of gypsum. The wavelength or the absorption feature that we're going to map now is this one here, which is typical of many sulfates, including gypsum. That's at about 1.75. Okay, time for a break again. Okay, the wavelength image has been created now. Let's have a look at the result. In a scatter plot viewer, so this is what the scatter plot looks like, and the gypsum rich pixels, they're shown here. Yeah, and the absorption feature at around 1.74, 1.75. Okay, we can also make a wavelength map to show the different wavelengths in different colors. I have to change again the range here. From 1.65 to 1.82. I click run. Okay, let's have a look at the result. This is the wavelength map that results. And the legend. And this shows that gypsum-rich pixels are shown in yellow, wavelength position, around here. We can check the spectra by adding the reflectance data as a shadow image. So let's click on one of the pixels here and see what we get. Well, you can see that we get a very clear absorption feature related to gypsum. Okay, so that works. What we'll do now, export this to Google Earth and display it in together with the other image in Google Earth. So from the wavelength map, again, I'm going to create a KML file. Okay, the rest of the settings are still right, so I click run. KLM file is created. There it is. Let's open this in Google Earth. And this is what we get now. So this is the previous image with illite and calcareous soils. And now we can see where the gypsum deposits occur. Yeah, so we can see gypsum here and here and here and here. So let's zoom in here, for instance. And you can see that there's abundant gypsum here along this slope. So this is most likely a big gypsum-rich mountain. And there are also quarries in this area where gypsum is being mined. So there's more here and more here and on this side of the image as well. Yeah. Okay. So with this view, I would like to conclude this tutorial. Thank you for watching. I hope it was useful, instructive, and that you enjoyed it. Hope to see you again. Bye.